All right, let's just dive right into it. Today, we're finally going to solve the mystery of why data actually takes time to travel across the internet. If you've ever wondered why a file transfer crawls or why your video call stutters even when you're paying for super high-speed internet, well, you are definitely in the right place. We've got a pretty packed agenda today. We're going to start with a quick hook and recap, dive into transmission and propagation delay, walk through a really great caravan analogy, bust some common points of confusion, and then wrap it all up with end-to-end delay and real-world lag. Let's get to it. Section 1, the hook and recap. So in Explainer 8, we talked about why a packet waits in a router's queue. But today we're asking a fundamentally different question. We're asking, why does physically pushing bits onto a wire take time? And why does a signal take time to literally cross a continent? And maybe most importantly, are they the exact same thing? Spoiler alert, they are absolutely not. Confusing these two is honestly the single most common stumbling block in computer networking. To ground ourselves before we pull all this apart, let's bring back our master formula. You might remember this. It shows the 4 types of delay that just naturally accumulate at every single router node along a path. We've got processing delay, queuing delay, transmission delay, and propagation delay. But today, we're laser focused on those last 2, transmission and propagation. Moving on to section 2, transmission delay, or pushing bits. Let's isolate that third variable. This is entirely about the physical, hardware-level act of getting your data from the router onto the actual wire. Looking at the formula, transmission delay equals L divided by R. L is simply the length of your packet in bits. R is the transmission rate of your link. Think of your standard 100 megabit per second Ethernet connection. Now, the absolute crucial point here is the units. If you divide a length in bits by a rate in bits per second, those bits mathematically cancel out. So what's left? Pure time, usually measured in microseconds or milliseconds. It's the literal time required for the router to push the packet out the door. Think about it like this. Imagine a train entering a track. The entire train is your packet, and the individual train cars are your bits. The time it takes from the moment that very first car starts moving until the very last car of the train physically rolls past the station platform, that is your transmission delay. It strictly depends on just 2 things: how long the train is and how fast the station can load those cars onto the track. Okay, section 3, propagation delay, or crossing distances. Because once that last train car leaves the station, what actually happens? Once those bits are fully on the wire, a completely different physical law takes over. We calculate propagation delay as D divided by S. D is the actual physical distance between router A and router B. S is the propagation speed of the link. And here, the speed is determined strictly by the physical medium. We're talking fiber optics or twisted pair copper wire. The speed operates at just under the speed of light, roughly 2 to 3 times 10 to the 8th meters per second. Fast, right? Picture a single pulse of light just zipping across a dark fiber optic cable buried underground. Here's the kicker. It doesn't matter how fast the router pushed the light into the cable. Once it's in there, it travels at the speed of light in glass. That journey across the actual geographic distance, whether it's just across the university campus or literally across the Atlantic Ocean, that is your propagation delay. Section 4, the caravan analogy. Now, I know microseconds and the speed of light can feel kind of abstract, so let's use a classic textbook analogy to translate this network math into the real world. Think of 10 cars traveling together in a caravan. These 10 cars represent a single packet, and every individual car is a bit. So they arrive at a toll booth, which represents our router. Now, this toll booth has a specific service rate. It can process and push through exactly 1 car every 12 seconds. Once a car passes the booth, it hits the highway, which is our propagation medium. Let's say the highway stretches for 100 kilometers to the next toll booth, and the cars travel at exactly 100 kilometers per hour. All right, let's actually do the math on the total delay from the first booth to the second. First up, transmission. 10 cars, processed at 12 seconds each, takes exactly 120 seconds, or 2 minutes. That's our time to push the packet onto the highway. Next, propagation. Driving 100 kilometers at 100 kilometers per hour takes exactly 1 hour, or 60 minutes. Add them up, and boom, it takes exactly 62 minutes total for the entire caravan to be lined up and ready at that second toll booth. Moving to section 5, the confusion buster. If you're still feeling a little tangled up by the math or the definitions, seriously, don't worry. We're going to break it all down side by side right now. This comparison brilliantly illustrates the divide. Just look at the dependencies. Transmission delay is entirely a function of your packet's length and the hardware's link speed. It has absolutely zero to do with the physical distance between the two routers. On the flip side, propagation delay is completely bound by geography and physics, distance and the physical medium. It has absolutely nothing to do with how big your packet is or how fast your Ethernet card is rated. Make sense? Let's bring it home with Section 6, end-to-end delay and real-world lag. Now that we've isolated a single hop between two routers, let's zoom out. In the real world, data travels across many routers. In a perfectly uncongested path, meaning, we can just ignore queuing delays for a second, the total end-to-end delay is pretty simple. It just multiplies our base nodal delay formula across n, which is the total number of links between the source and the destination. Through this multi-hop progression, you can really intuitively see how data actually moves. At the very first router, the packet is processed, queued, pushed onto the wire, and then it travels. Then it hits router 2, and the exact same store and forward process happens all over again. Crossing a continent literally requires adding up the pushing, the transmission, and the traveling, the propagation, at every single router along the entire path. And you know what? This perfectly explains why we actually experience real-world lag. When you're on a voice or video call with someone on another continent, that high propagation delay is exactly what causes you to accidentally talk over each other. On the other hand, if you're trying to download a massive file over a low-speed connection, your transmission delay dominates, completely throttling your download. And when packets arrive with varying end-to-end delays, we get jitter, which completely ruins audio quality unless your receiver buffers it perfectly. We've spent today exploring the delays of a smooth journey, basically assuming our packets always find room on the track. But that leaves us with a pretty provocative thought. What actually happens when the network gets too congested? If traffic intensity gets way too high, the router's queue fills to absolute capacity. So when a brand new packet arrives and there's literally nowhere for it to go, what does the router do? Well, it just drops it. And that brings us right to the topic of our next explainer, packet loss and throughput. See you there?